Hey there guys, today we're going to prove that the derivative of e to the x is indeed e to the x. This is going to be a general outline proof of how it's done. It may not be as rigorous as you want it to be if you're trying to do this in something like real analysis, but hopefully it gives you a perspective on how the derivative of e to the x is derived. So, in order to prove this, what we want to show is that the derivative of e to the x is e to the x, or it's equal to f prime of x. So if we go back to the main idea definition of the derivative, f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x divided by h. So from this definition of what the derivative is, we're going to show that the derivative of e to the x is e to the x. So if we start with f of x equals e to the x, and we put it into the definition of the derivative, f prime of x equals the limit of h approaches 0 of e to the x plus h minus e to the x divided by h. So we put x plus h because, right, it was f applied to x plus h. So before where that was e to the x, for x you put in x plus h. So that's how we get that. So from there, what you can do is, because that's e to the x plus h, you can simplify this into e to the x times e to the h minus e to the x divided by h. So from there, note that if things have like bases, if their exponents are being summed together, then that's just equal to the base of the product of the exponents. And yeah, note that they're in the real numbers, because with complex numbers, things happen a tad bit differently. And from there, what you can do is you can factor out an e to the x, because both terms in the numerator has the term e to the x. So what we have is the limit as h approaches 0 of e to the x times e to the h minus 1 divided by h. And from here, even though I didn't write it, I'll explain it. So the limit as h approaches 0 of this right here will be equal to the limit as h approaches 0 of e to the x times the limit as h approaches 0 of e to the x minus 1 divided by h. So that, because those are a product of two things, so the first term, e to the x, is not dependent on h at all, right? So when h goes to 0, e to the x will be unchanged. So we can just bring that out of our limit, because it's no way dependent on h going to 0. But we have this second part, the limit as h approaches 0 of e to the h minus 1 divided by h. So with this here, we know that this has to be a constant, because either this will be a constant or it will be undefined, which we know that it won't be undefined because, first off, for this to be defined on this, well, I guess, see, the best way to kind of explain this is that you can write a Taylor series for e to the x, so I know that you can do this. So from here, what we have is the limit as h approaches 0 of e to the x minus 1 divided by h. So we can assume that this is going to be a constant. We don't know what it's going to be. It could be 0. Let's say that the derivative of e to the x is 0. That's obviously not going to happen, but in terms of solve this, we have to assume that it's going to be an arbitrary constant. And I keep the limit on the right hand side as h approaches 0 to c, because the limit as h approaches 0 to c will just still be c, so I could have wrote that as just c, but it's important for that to stick around so that you can keep up with what's happening here. So c obviously exists in the reals, because we don't want to say it exists in z, because maybe our constant will be irrational, or maybe it will be a non-integer. But from here, where we go is that with the algebra, you multiply through by the h. So we have the limit as h approaches 0 of e to the h minus 1 equals the limit of h approaches 0 of c times h. You continue this through, bring over the 1, so we have c h plus 1. And then from here, what you do is you raise both, you raise both sides to 1 over h. So that's going to cancel out the h on the one side and make this second part up to limit as e equals limit of h to 0 of ch plus 1 raised to the 1/2. And here I put e to the first because even though that exponent isn't written there, it's assumed to be to the first power. So from there, what we have is the limit as h approaches 0 of ch plus 1 to the 1/2 power as h approaches 0. But let's try something new here. Let's say that h is equal to 1 over n, okay? So if we plug this in, we get e to the 1 equals the limit as 1 over n approaches 0 of c to the n plus 1 to the n. So, and now you have to think here. So, when is 1 over n going to approach 0? Well, it's going to happen when n gets really big, right? Or n equals infinity. So, the limit, so by writing 1 over n goes to 0, that's the same as n is going to infinity. So you have e to the first equals the limit as n approaches infinity of c to the n plus 1 over n. And if you remember this is the limit definition of what e equals. And what's important to notice here is that, for example, if this was e to the x, it would equal the limit as n approaches infinity of x over n plus 1 to the nth power. So that c there is actually equal to what the exponent on e is. So from here what we get is that c equals 1. So we know that c equals 1, and from that we had that f prime of x equals e to the x times e to the h minus 1 over h, but we showed that that's going to be equal to 1. So from that we get that f prime of x is e to the x times c, which is equal to e to the x times 1, which is equal to e to the x. So from that, we did show that we want to show that d dx e to the x equals e to the x equals f prime of x. So that completes the proof of how the derivative of e to the x is e to the x. So probably if you're watching this video, you're probably doing real analysis, I'm going to assume, and there are, this is an okay proof for proving e to the x, but I may do another video on if you're talking about continuity and the epsilon delta definition. But in terms of getting a general idea of how this proof will work for what e to the x, the derivative of e to the x is, this is a pretty good way of showing it. So that will be the end of this video. I will catch you guys later.